I said not as Grothendieck would have liked to see it, but more algebraic than we've seen it over the complex numbers, so that actually now we know, we've seen what is the fundamental group and tame fundamental group for also, well, for all varieties, normal varieties, and normal integral varieties in characteristic 0 and in characteristic P. And I recall this, so what was it? So if you have K a base field, and then you take X over K some normal, I will say GR hyperbolic curve, or maybe hyperbolic GR, hyperbolic GR curve. Remember that this means that this sits into a smooth completion x0. So this is the smooth completion. And R is simply the cardinality of this minus this here, where X bar is the bar means base change to the separable closure, algebraic closure, which, well, this cardinality does not change whether you go, if you go further. And then we had the canonical exact sequence. 1 goes to pi 1 tame X bar, goes to pi 1 tame X, goes to GK, goes to 1. In particular, so this is hyperbolic. Part of the hyperbolic is that it is geometrically integral, yes. So we had this exact sequence. And remember that Grothendieck specialization theorem tells us something about this guy, which is then finitely generated, and it is a quotient of, so Grothendieck specialization theorem tells us the following, that this is as a, well, PGR completed, goes surjectively onto P1 tame X bar. And this is an isomorphism at prime to P level, prime to P, yeah, level, okay. That means via topology and complex analysis, we understand this guy, well, at least the prime to P part very well. And in general, we do not know what it is in characteristic P. In characteristic 0, because tame equals the usual, because there is no inseparability, no wild ramification issues. Okay. Now, naturally, so we define this pi 1 tame and so on much more general than for hyperbolic curves, but we'll mainly speak about this. Now today, so before I start, I go to announcing the Grothendieck conjecture, I will say first, so a definition, which is maybe something not very precise, yeah? So let's be X given scheme. Nice scheme, yeah. So that we can speak about a fundamental group, yeah, and then maybe P some property of X. Well, this means actually you take all the schemes, and now this P is the properties about all the schemes, yeah, which we name. For instance, if this is the category of all the curves of genus or of type hyperbolic curves of type G R, then this is the property that actually X is a curve of X0 has genus G, yeah. Okay, then we say that P is an Anabelian property if P can be recovered from pi 1 of x, or maybe I would say is a tame Anabelian property. So pi 1 tame, I write from here, yeah. Pi 1 of x. Yeah, can be recovered from pi 1 of x by a group theoretical recipe. Now, this is something important which hopefully everybody can digest. That means I have something which I have in the language, or in the language of groups. I have something where I'm allowed to use only what tells what is formulable in the language, well, in terms of groups, and then I apply this recipe to pi 1 of x, and the answer can be yes or no. Hopefully that is decidable. And then if the answer is yes, then the scheme X has the property P, and if the answer is no, the X does not have the property P. Maybe examples, and then we will be. Let's say that X are fields, well, are spec of K, yeah, with K fields. Yeah, then being, so, and let's say that P means K is real closed. Then this is an Anabelian property. Yeah? So then P is an Anabelian property. And what is this? This is the famous theorem of Artin-Schreier, yes? So Artin-Schreier. And the question is, okay, can I say more about K? Yes. Actually, one can recover really the ordering on K and so on, namely the set of what is this Anabelian property? So P is equivalent to, this is equivalent to GK is isomorphic on what? So pi 1 of x isomorphic to Z mod 2. Yeah. If this is the case, then K is and then I can recover lots of properties about this. For instance, I can recover the ordering and so on and so forth. Yeah. Another example, maybe 2. Let be X complete curves over K containing the complex numbers. Then the property P X has genus G is Anabelian. Yeah, so how to do this? Maybe over K equals K bar containing the complex numbers, yeah. So what is the property of this? Well, this means exactly because P is the same as pi 1 of x has 2 G generators. Yeah, so topological generators. Okay, so these are the most trivial properties of. But now, well, I can give you another example which is not at all trivial.
Are you allowing X to have singularity?
No, I say complete hyperbolic. Yeah. So complete. Here I don't have to say that. Complete smooth curve. Yeah. Over this. Now 3, let be X finitely generated infinite fields, and let be P should say that the isomorphy type, yeah, the isomorphy type of X is, and now you fix one of these many finitely, yeah, is K, where this guy is fixed, the fixed field. Now, the theorem which I mentioned during the first talk tells you that actually, so this theorem by many people, so Neukirch, Uchida, and so on, tells you that actually P is Anabelian. Yeah? So P is Anabelian. Maybe, yeah, not this, but this then. Yeah, so what is this? This is the pure inseparable cover. Yeah, okay, thank you. Got it. Yeah. And so, okay, now we are in the, we have seen some examples, and now we're in the shape to say, to announce the Grothendieck conjectures. So, yes? Maybe. No, maybe that's more. What I say is that actually you have a group, so you have only the fundamental group, and then you have a group theoretical recipe, and you run this group theoretical recipe, and if the answer is yes at the end, you have the answer to your question. In this concrete case is, if where I'm, yeah? What is the recipe? For instance, the recipe is if P1 of X is isomorphic to Z mod 2. And now you will ask me, how can you recover then?
He doesn't want, for instance.
Oh, no, I don't want to get into this. You can formalize this completely, yeah? Namely, you take, so you could speak in the following, but maybe, no, I don't want to get into this. Actually, it is formalized in the thesis of Jakob Stix. Yeah? So you can think of this as a functor from. You make here assertions about schemes, several assertions about schemes, and then you simply take a functor from the category of fundamental groups into that, yeah, into that category. Well, now, but you have to formalize this, yeah. I will. So maybe this the best is you can do this by examples. Yeah. A group theoretical recipe, for instance, we'll see actually in the working groups. My student maybe will show you. If you have a finitely generated infinite field like here, and you know the Galois group, then there is a group theoretical recipe by which you recover the cyclotomic character. Yeah. And this group theoretical recipe, okay, maybe. Another further examples, yeah. Take a global field. Then Neukirch's theorem gives you a group theoretical recipe in order to identify all the decomposition groups of all the places. And this group theoretical recipe is a closed subgroup of the absolute Galois group of Q. Okay, stay with Q. A closed subgroup of the absolute Galois group of Q is the decomposition group at the prime P. P is a fixed prime, if and only if it has the following properties. It is pro-solvable. It has cohomological dimension 1 for at least 2 primes. And it is maximal with these two above properties. Is this a satisfactory group theoretical recipe? Yes. And I said it has cohomological dimension 2 for at least 2. Well, okay. I said 1. Oh, sorry, 2. Yeah. Yeah. Pro-solvable has, thank you, has cohomological dimension, yeah. So this is a prototype of a group theoretical recipe. Yeah.
So I think the point is that what you're doing is stronger than just abstractly saying that P is determined by the isomorphism class of the fundamental group, because you're explicitly saying how you determine whether or not P is satisfied given the groups. I mean, I don't know if that's what you're asking.
Yes, sir. But really,
You might not be requiring something as fine as the isomorphism class.
well, I think that, yeah, we can discuss later about this, yeah. So it's like, Björn, it's like trying to explain somebody that model theory is interesting. Actually, after the person is, exposed to that, realizes, yeah, these guys have something to say. And I think, while teaching undergrads, I think one every time has this experience. Is it really interesting what we are doing? Eventually, after they learn enough mathematics, they realize, yeah, so some of them realize it's interesting. Okay. Now, I will say now, so the Grothendieck's conjectures for curves, Anabelian conjecture, yes. Anabelian for curves. And he says the following, so given K a finitely generated field, and field K, and given X to K hyperbolic curve, then so one has the following. So one has the first part of is that actually the isomorphy type of xi. So this is the pure inseparable, maximum inseparable cover. Maybe I should say here further notations. So xi goes to x is the maximal pure inseparable cover. And also concerning notations, now I have to say more and more. Another one here, for every m in Z and x as there, x over k. I will stay further with hyperbolic curves. Then if characteristic of k is positive, say p, then we denote by, then this xn goes to k, and xn I goes to ki are the nth Frobenius twists. The relative nth Frobenian twists. Frob twists. So I will not say, okay, so what does it mean? So you have here k, and here is Frob, k, and here is x. Then there is something which you can fit into this diagram, and that is xn. Yeah? And now it turns out, pardon? To the n. Thank you. Yeah, now it turns out that, well, this guy, if you go like this or like this, that is not a, but this is a k scheme, yeah, so. And then this is the Frob twist, yeah. Should I give it a name? Phi n. Yeah, so. Yeah. And, okay. So now what is this? This is actually simply acting on the coefficient. So actually when you have an equation, you can act on the points, or you can act on the geometric points, or you can act on the coefficients. The Frobenius n is acting on the coefficients. Okay, now I come back here. So the isomorphy type of xi is Anabelian. Is an Anabelian property. Is an Anabelian property. Yeah, and moreover, now first I will take, say, I will call it isom form, given, moreover, given y goes to k, some, and I say now hyperbolic again, hyperbolic curve, one has the following. Every isomorphism, so every isomorphism, every isomorphism. So this is a group theory, so group isomorphism, yeah? So group isomorphism, maybe large phi, defined on P1 tame of X with values in P1 tame of Y, is defined by some isomorphism, well, of schemes. Xi goes to Yi. Yeah, maybe here is a phi. Now, what I mean by this, so by the functoriality properties of the fundamental group, if you have an isomorphism here, then up to inner automorphism, you can, that induces an automorphism or an isomorphism between the fundamental groups. And if we take our fundamental groups as having, so you see that actually I never speak about a base point here, and now I don't even recall whether I mentioned it here or not. So my fundamental groups have values in the category of groups with outer homomorphisms as morphisms. In particular, the relevance of base points then disappears. Yeah, and so that is the, yeah. Where xi is not a, well, it's not of finite type, but we know what it is, yeah? That is not a scheme of finite type, but it's a very decent scheme over K, or over Ki. Yeah, right, so what is that? Well, if you take, for instance, if your curve is P1 minus 3 points, what is xi? Well, it's the spectrum of, not of K of T with T and 1 over T inverted, but you take all P powers, P roots from T, that's it. Yeah? Okay, maybe I should give an example here. Yeah? So suppose that X is P1 minus 1 infinity 1, 0, T and lambda. Yeah. Then what is first xi? So what is then x? Well, x is spec, and now here we have our preferred coordinate, yeah, so t. Then this is simply spec of, and here is k, yeah? That is spec of t, and, pardon? So, yeah, you know that actually this is 1. No, this is 1 here. 0, 1, infinity. 0. Yeah, lambda. Okay? Yeah. So now what is this guy? So it's t, and I have to invert, I think, t and 1 over t minus 1. Yeah. Something like this. And lambda, yeah, and 1 over t minus lambda. Then what is xi? Well, this is exactly the same spectrum, but that is spec of k, and now I have here 2t to the p to the minus infinity, yeah, well, yeah, and yeah, and then the rest is the same, yeah. So it's the same, but adjoined here 1 over ki, and then here t to p to the minus infinity. That means you take all powers from p. And what is xin? Now here I have to, my recollection is that actually this is again ki, but here it's 1 over t minus lambda to p to the n, yeah? And the rest is the same. I never know whether it's p to the n or p to the minus n. I think it's p to the n, yeah. Because you act on the coefficients, yeah. Okay. Now we have some examples to see what is. Okay, so the conjecture is that, moreover, so given an isomorphism between the tame fundamental groups of two hyperbolic curves, then this comes from an isomorphism of the pure inseparable covers. And this is more or less unique. So it's unique up to Frobenius twists, yeah? And phi, so this phi is unique up to Frobenius twists. Okay, now B, what should be the home form? Well, exactly the same with the difference that now I ask this only to be an open homomorphism, and then I ask that this should be a dominant map, yeah? The same, well, given every open group homomorphism, maybe phi defined by pi 1 tame of x with values in pi 1 tame of y is defined by some isomorphism of schemes phi defined on xy with values in I, which is again unique up to dominant, so this is some dominant morphism. Yeah? Morphism of schemes, which is unique up to Frobenius twists. Okay. And I could say here now, so this here, you could say that it is the absolute form. So there is somehow a kind of asymmetry in these assertions. Namely, if you start with a curve x over k, then from that you have this exact sequence. Well, this the canonical projection from the pi 1 into gk. Now, nevertheless, here we forget about that, and we view this as an individual group because we are after some Anabelian property. But now you could bring more structure into it, and namely, you could allow or ask what do isomorphisms which are compatible with the projection. Yeah, that means which are compatible with this projection from pi 1 to gk. And then you would expect, then maybe we can recover even this. Well, maybe not this, because again, taking pure inseparable covers, this is a general story, you can't recover. These are not seen by the Galois theory. And so that is maybe the relative form. Maybe this is not more over, so no. Actually, here is more over. And here is the absolute form. And now I have the relative form. Well, I will not, so it's like before, so context as before, context as above. Then, so every gk isom phi defined on p1 of x goes to p1 of y. And what means gk? So that this should commute with the canonical projections here to gk. So this is actually a gk isom, but I don't put it anymore. Comes from some K isomorphism, well, Ki isomorphism. Now I say phi defined on, and the point is now the fundamental group does not see Frobenius, absolute Frobenius twists, and does not see relative Frobenius twists. Therefore, maybe X is not isomorphic to Y, but some Frobenius twist of this, and this is actually the point. So some Frobenius twist, yeah, yi for some m. Yeah. And this is unique up to Frobenius twist, up to absolute Frobenius twist, yeah, and phi is unique up to absolute Frobenius twists. Well, up to Frobenius twist. Okay. Once again, in characteristic 0, this is not, so the Frobenius twists do not show up at all. And you can forget then tame, and you can forget I, and then you have absolute assertions, yes? And maybe B, now the same, the home form. So this was naturally the isom form here. So home form, like before, every open GK home, phi defined on P1 of X goes to P1 of Y, comes from geometry as above. Comes from a dominant phi defined on Xi, Yi as above. Okay, as above. Okay, so maybe I should say some few words about this. Actually, these are quite strong assertions, yeah. Actually, so Grothendieck, I do not know where he got this inspiration, but actually one can ask this question very often in his case. Had the intuition that actually, because of this strong, so you look what do you have? Well, in the absolute case form, you have only this. This is what you have. Yeah? And now the point is, he says that actually this sits naturally in this exact sequence. And then here you have a very strong interaction between the arithmetic, which is reflected in the absolute Galois group of the base field, and the geometry, which is quite complicated because we said hyperbolic. And then this interaction actually singles out the fundamental group of the curve, singles out the curve through its fundamental group among all possible fundamental groups.
There's another conjecture also, which is part of this, the rational function.
I come to that, yeah. Okay, so it is a lot known about this, and actually in my notes, here I have to say something important. Actually, the version of the notes is not the final version of my notes. That is the version of, I don't know, which is maybe 4 days or something like this, older than the final version. And so when I will go back, I will put on the web the final version, because I could put that, I could do that now, but in that maybe there are spelling mistakes and typos and so on, and from here, from this place here, I cannot do anything in our, yeah. So that means if you are still interested, or if you want to have this in among your in your library, then please do it maybe 1 week. After 1 week, then the final version will be on here. Okay, now I will come. So these are the so-called Grothendieck conjectures, Anabelian conjectures for curves. Now I come to, well, when do I have to stop? At 11, yes? That means 5 past 11. Okay.
What does that mean?
Sorry.
What does 5 past 11 mean? This is German time, right?
That's cum tem, that is fine.
I remind you that you're
Okay, now, okay, then I still have to use the last 5 minutes, which I do not have, in order to make another comment. Actually, when started Grothendieck doing these things? Well, it was at the beginning of the 80s. And this is part of, so what I'm saying here is in a letter to Faltings, but he was giving thoughts already before that, and it was starting building this, what we call now Grothendieck program. Part of it is a Schism program, and so on. Program. And I think that one of his main motivation was actually to prove the model conjecture. Because he had some ideas that actually using fundamental groups and so on, you might be able to characterize rational points. And now here is really some philosophical little point. The algebra and geometry, what we are doing, I mean this algebraic geometry, yeah, are discrete. So these live in a discrete world. And then everybody tries somehow to use analysis, I mean to periodic fields or true analysis, because these guys have a rich topology, and then you can understand more doing analysis. And now, one of the points which maybe he does not tell, but he had maybe in mind is, if you could encode arithmetic and geometry in the fundamental group, this guy is compact, then all possible things which you speak about play now in a compact world. That means, usually what is this? Usually when you have infinitely many objects of the same type and so on, they must have accumulation points. And now concerning the model conjecture, if you prove that there are infinitely many points, and if you have a description of the points inside the fundamental group, then there must be accumulation points. Now imagine that if there is some justice in the world, then if you have something which is infinite, then maybe that should be a perfect set or something like this. At once you have too many points. It can't be that. I think that after Faltings proved the model conjecture, then this problem somehow, so the point of view became obsolete, but nevertheless, it might still be very significant for what for questions in arithmetic geometry. And therefore, I will speak now, I will present the section conjecture. And then last time I will make a brief account of what is known about these conjectures. And I will also pick a little bit on Grothendieck, because fortunately, these Anabelian phenomena turns out that they are almost ubiquitous when the geometry is sufficiently complicated, and that here there is a lot of arithmetic is not significant. Yeah, at least in some contexts. Okay. Now the next step is the section conjecture, and I have preparation. We are in the situation from there with an hyperbolic curve and the completion and so on. Yeah. Okay, so x in x0, hyperbolic GR curve. Then you have, as usually, the exact sequence. Now I have to write it once again. It is true even without tame here, but I'll keep it now. Yeah. And now let's pick a point. So x be a k-rational point in x0. So maybe there are no such points, but suppose that there is such a point, yeah? Okay, then you do the following. I will speak now for people doing, being familiar with the birational version of this. So you have here the function field of this, which is the same as k of x. Yeah, and then you have here the separable closure of this guy. Now you take the point, maybe this should be k of x here, and here is k of x0. And now you take this point x in of k of z. Well, this corresponds to the corresponding Weil prime divisor. By the way, Weil prime divisor, yeah? This is a place of the function field. And then you take a prolongation of this guy to the separable closure. And then you have here a big decomposition group, ZV. I will call it simply V. Yeah? ZV. And so what is this Vx? This is a discrete valuation. And now recall that's what is written in all possible books about valuation theory. This has the following property. So you have the inertia group in V, and the quotient field of this by this is simply the epsilon Galois group of the point. But X was a k rational point, therefore this is the same as GK. Yeah? Okay, so goes to 1. I have this. And now there is a, well, I think that even everybody could prove this theorem, but there is a fact proved in for general valuations that actually this projection here, maybe PV, has sections. Yeah, so this has sections, SV. Yeah, so fact. Here, the canonical projection ZV goes to GKX, kappa X equals GK, has sections. Always. Sections, SV maybe. Yeah. So I call this projection PV. So there are sections. Well, in other words, the inertia group which sits here has complements. Yeah. Okay, and now you do the following. So now I have to erase this. Sorry for this, but because here is my picture. Yeah. Now this guy is a quotient of GK of X, and then here this is the canonical, and here it's equality. And while this is actually GK bar of X, yeah, and this is a quotient of this, yeah, like this. And now what did we see before? Well, there are sections here. SV. Now, if you go like this, you see that actually this has a section. Yeah, so now you go particular. So call this maybe PX or projection. Yeah, maybe it's too heavy on PX. That means projection X after SV defined on a GK with values in P1 TX is a section of P of the project, simply of Pr. Yeah. And you see, so this is really only almost a kind of abstract nonsense. Well, you have to do something, and to prove that that has sections and so it's a little bit of work. Yeah. So with
You don't need this big point in X, right? I mean.
no. This is a point in X0.
I know. Okay.
Pardon?
Oh,
Okay.
in X0?
But why-
It's a
why-
point
why
in
is-
X0.
why are there many X?
Pardon?
Okay.
So, great. And now, so maybe remark. One, if X is actually in X, yeah, then what is the image of, well, so then what is this I, what is TV? What then pr X of TV equals 1. Yeah, why? It's because this classifies unramified covers of X and the point in X and so on. That means this is, yeah, and X gives rise, so yeah, and the projection of the decomposition group is then really projection of the section, yeah? So it's projection of SV of GK only, yeah? That means that's really, so it's, yeah, okay. And the conjugacy class of, no, maybe I should call this section SX. Sorry, this is, yeah. So this equals SX. So SX is simply the composition, yeah? So maybe this. Oh, I have here then SX equals this composition, yeah? So per X after SV, yeah? Okay, and then this is simply SX of GK, yeah? And then this, the conjugacy class of SX in GK determines, well, is determined, yeah, is completely determined by X. Now, what happens if this is not the case? No. So, second, if X is in X0 minus X of K, then there are many more other sections. Then there are, I simply say many sections which do not come. So, well, why? So there are many sections because actually this section here, so there are lots of sections here, then the projection, so I say, then, sorry, then the point is that the pre-X of the decomposition group, of the inertia group, TV, is different from 1. Well, this is actually a characterization of the fact that the point is, there is ramification there or not, yeah? And one can say that there exist many sections which are not conjugated, yeah? Arising as above. Arising as above. Which are not conjugated, yeah, so. Conjugated, fine. Now I erase the picture. Okay, now actually I could tell you now what says the section conjecture. The section conjecture says that if your base field is infinite and the curve is not defined over a finite field, that means you still could have K infinite, but the curve could be defined over Fp, yeah? Then all the sections arise in this way. Yeah, so section conjecture. I do not exaggerate. Okay, out in this section conjecture. That was okay for curves. And now here it's section. So in the above context, one has first birational form, all sections of GK of X goes to little gk. I have to say, in the above context, suppose that, suppose that K infinite and X not defined over a finite field, not isotrivial what is this? ISO something. ISO not defined over a finite field. Over a finite field. Then the birational form says that all sections of this arise in the way indicated. Actually, yeah, so it was here the picture. Sorry that I erased it. Yeah, so you had 1 goes to TV, goes to ZV, goes to GK, goes to 1. And so this was over a point, ZV, here. Yeah, so this V was some prolongation over some Vx. And then the conjecture is that all possible sections arise in this way, which was indicated. And second, the curve form. All sections of pi 1 tame x goes to gk arise in the way indicated, yeah? Well, in the way indicated, coming from points, yeah? Coming from some points, some x in x0, k. And here in the way indicated, so coming from x in x0, k. So this is the section conjecture, and now maybe here concerning remarks. Yesterday, Makoto spoke about a point, tangential base point. Actually, when the point x is in here, and k has characteristic 0, then there is a nice description of the space of conjugacy classes of sections, and that is, so maybe remark 3, and then I'm done. Yeah, so remark 3. So remark. But this remark is remark 3, yeah, there. If characteristic of k equals 0, then the space of, yeah, and x is not in x of k, well, x is in x0 minus x of k, then the space, so then the isom classes, the conjugacy classes of section, conjugacy classes of sections above x, yeah, in bijection with h1 gk z hat 1. Yeah, that means, and these, if you want, an element from here, g little k. Yeah. So now, if you want, an element from here is a tangential base point. Yeah. So among other things, so question here. So this is a question, yeah. Tell me which element of H1 GK Z hat 1 defines 0, 1 in the case x equals P1 minus 3 points. Yeah.